Hi, everyone. Welcome. I'm Jennifer Gunn. I'm the director of the Institute for Advanced Study and a historian of medicine, and I'm happy to welcome you all to IAS Thursday. This is actually the last IAS Thursday of the semester, and we're ending on a high note, I think. Before we get started, I want to acknowledge that wherever you are joining us from today, we are all located on the traditional, ancestral, and contemporary lands of Indigenous people. The University of Minnesota's Twin City campus resides on Dakota land ceded in the treaties of 1837 and 1851. The Institute for Advanced Study acknowledges that this place has a complex and layered history, and a land acknowledgement is one of the ways in which we work to educate the campus and community about this land, our relationships with it, and with each other. So the IAS is committed to ongoing efforts to recognize, support, and advocate for American Indian nations and peoples. Well, we have a few announcements crammed in here at the end of the semester. There are several new funding opportunities that are available. And guess what? You don't have to put in a proposal before the end of the semester. So the IAS Research and Creative Collaboratives applications will be due Monday, January 31st. So there's more information about this on the IAS website. And also the Imagine Fund special events grants are now going to be administered through the Institute for Advanced Study, and the deadline for grants that will be able to be used in spring of 2022 the deadline will be February 2nd, 2022. We are also, that is the IAS, is hiring a graduate student as an editorial assistant for the Open Rivers Journal, Rethinking Water, Place, and Community. So this is a great opportunity, as well as it's actually a paid opportunity. So look online for more information, and the priority application for deadline for this is tomorrow, just FYI, but the position is open until filled. And stay tuned. Coming on our website will be our programming for spring 2022. And if you would like to get a weekly newsletter from the IAS, which will remind you about upcoming events and opportunities like grants, fellowships, etc., please send an email to ias.umn.edu, sign up on our website, or Abby Travis will be putting the link in the chat to be able to sign up for the newsletter. As is the case with life in the virtual world, we have a few Zoom technical instructions for you. Zoom auto captions are enabled today. And if you want captions, click on the live transcript button in the bottom right, on the bottom right Zoom menu bar. If you're on the desktop or a laptop, it should be on the bottom right. If you're on a mobile app, it's probably in the upper right. We also will have time for, and then you have to click show subtitles or view full transcript, sorry. We'll also have time for audience questions at the end of this event. If you have questions for Kate Marvel at any time during the presentation, you can enter them in the Zoom Q&A feature, which is also located on the Zoom menu bar. And if you want to introduce yourself or share resources, you can do that in the chat function, which is also on the Zoom menu bar. So be sure to select all panelists and attendees when you send your message in chat. Let me just reiterate again, questions for Dr. Marvel go in the Q&A box. Anything else goes in chat. Okay, it is my very great pleasure to introduce our speaker today, Dr. Kate Marvel. At the IAS, every semester, we try to bring in a speaker or two who are suggested by the residential faculty fellows. And Dr. Marvel is the suggestion and choice of geographer Scott St. George. Dr. Marvel, as you will soon learn, uses climate models, observations, paleoclimate reconstructions, and basic theory to study climate change. Her work has identified human influences on present-day cloud cover, rainfall patterns, and drought risk. She is also interested in future climate changes, particularly climate feedback processes and the planet's sensitivity to increased carbon dioxide. Dr. Marvel teaches in the Columbia University Masters in Climate and Society program, and she writes the Hot Planet column for Scientific America. She's also leading the Climate Trends chapter of the National Climate Assessment, and you're welcome to ask questions about that as well. It's not usual that we get somebody who's named one of 15 women who will save the world by Time magazine. And Dr. Marvel has also been profiled by the New York Times and Rolling Stone. In her 2017 TED Talk, Can Clouds Buy Us More Time to Solve Climate Change, has been viewed over 1 million times. So before becoming a climate scientist, she received her doctorate in theoretical particle physics from Cambridge University, where she was a Gates Scholar. So welcome, Dr. Kate Marvel.
Hello, hi, thank you so much for having me, and thank you for that very kind introduction. I am going to go ahead and share my screen right now. All right, so I am going to talk today about drought conditions in the Southwestern US, Southwestern North America. I want to talk a little bit about some of the things we know for sure about drought and what we can expect in the future. But I also wanted to give you a little bit of a preview of some new research. So this talk will be a mix of some very robust projections and some new stuff that is perhaps a little bit more speculative, but I hope will be provocative or at least start conversations. So to begin, we know that the Western United States is in a drought. It's in a fairly protracted and severe drought. And this matters. The consequences have been severe across sectors: agriculture, transportation, drinking water, infrastructure. And so it's really crucial to understand the drivers of this particular drought. And also, what do we understand about drought? Will this end? What will the future of this region and other regions look like? So we want to know what to expect. How is drought risk in this region going to change in the future? What do we actually know? So to see the future, unfortunately, we don't have any observations. Observations of the future, as the GFDL scientist Tom Knutson said, are not available at this time. So instead, to see the future, we have to use the output of sophisticated general circulation models that simulate the entire Earth system. There are about 30 of these models scattered throughout the world, developed by large modeling groups like NASA GISS, where I sit. But these 30 modeling groups are all participating in something called the Coupled Model Intercomparison Project, Phase 6. What this is basically a coordinated suite of experiments across the world's climate modeling groups. And this is generating a massive amount of data, about 50 petabytes of data. So this is an incredible resource, but it's also kind of a fire hose. And it's a really interesting proposition, really interesting research agenda to pick through this 50 petabytes of data and try to see what is robust across these models. What do we know for sure? And where are there uncertainties? Where do they disagree? So we know that these different climate models all project different futures. Sometimes those futures are slightly different from one another, but sometimes they are very different indeed. This, for example, is the climate sensitivity in the CMIP6 models. That's the temperature response to the doubling of carbon dioxide. So I want to stress that the inputs to all of these models are exactly the same thing. We're just abruptly doubling carbon dioxide in the atmosphere, letting the temperature come to equilibrium and seeing how much it warmed. And these models are projecting things ranging from between 1.8 degrees Celsius of warming fairly moderate, fairly muted, to 5.6 degrees Celsius of warming, which is absolutely catastrophic. Now, we have reasons to think that these extremely high climate sensitivity models here in the yellow are perhaps less credible in light of evidence, in light of paleoclimate evidence, recent historical evidence, and also what we know about the basic physical processes underlying the climate system. But that is a story for a different talk. What I want to stress here, though, is that even in the presence of model disagreement, some projections are reasonably certain. So let's start with the basics. Moisture supply in the form of precipitation and moisture demand in the form of evaporation. We want to know how these things are going to change in order to make planning decisions. But we don't just want to know how their mean state is going to change. We don't necessarily just want to know how the total amount of rain or snow falling on a particular area is going to change. We also want to know changes to the seasonal cycle. When are we going to get the bulk of rainfall? When are we going to get the bulk of evaporative demand in the future? And the models in some regions actually give you very coherent projections indeed. So even though I'm talking about drought, I want to stress here that no climate model really tends to project robust decreases in precipitation. We think that almost nowhere across the continental US are we going to see really robust, really large scale decreases in rainfall. In fact, in some regions, the climate models project fairly robust increases. So in particular, in the Pacific Northwest, we are going to see increases in rainfall. And those increases are going to arrive primarily in the wet season, in the winter. We also see fairly robust changes in the timing of rainfall, with peak rainfall coming earlier in the central and southwest. Now, evaporation, the climate models project fairly robustly increases in the northwest and the peak in many regions, the peak of evaporation arriving earlier. And that, we think, in large part is a vegetation signal that spring is coming earlier, allowing plants to green up sooner and allowing them to use more water and therefore increase the demand for evaporation and transpiration away from the Earth's surface. So precipitation and evaporation are really only part of the drought story here. Because when we talk about drought, we don't necessarily mean meteorological drought. We don't necessarily mean just an absence of rainfall. Drought has many different definitions, and different definitions are appropriate for different uses. So for example, take hydrological drought. Hydrological drought is usually defined in terms of runoff. And this is a variable where shifts in the seasonal cycle really matter. So in the West, in the western portion of the continent, we project decreases with runoff. We project decreases in runoff, except for that very southernmost portion of the region. Increasingly, we're going to see peak runoff shifting earlier and earlier in the season, and the decreases in runoff being largest in the season of maximum runoff. And all of these are really in accordance with a single story. We don't project a decrease in wintertime precipitation anywhere, but what we're going to see in a warming world is much less of that wintertime precipitation falling as snow. So we're going to see a real change in the ratio of rain to snow in the future warming world. And that's fairly intuitive, but that does have long-term consequences for hydrological drought, for runoff, especially in regions that rely on the snowpack. Now, when it comes to agricultural drought, what's the soil moisture doing? That's where the story gets a little bit more complicated. Climate models fairly robustly project drying of surface soil moisture everywhere. So that's the drying in the top few layers of the surface of the soil. So especially in the Western US, the climate models are projecting decreases in the surface soil moisture. And what that is largely a temperature signal. This is going to be driven by warming. Warm air is thirstier air. And so we're going to see increases in evaporation away from the surface in the future as the world gets warmer. However, when you dig literally a little bit deeper and you look at the soil moisture throughout the column, this is really important because this is where the roots of many plants are. So soil moisture in the root zone, it's a really different story. there are a few very clear trends overall. In the Northwest, we're going to see an increase in wintertime precipitation, which moistens that soil column in the winter, but then warming in the summer will dry it out. Whereas in the Southwest, soil moisture decreases throughout the year with the largest declines in the winter and early spring. So the projections when it comes to column soil moisture, things that deep roots really care about, we really don't have a coherent story here. And when it comes to projecting agricultural drought risk, the drying of soils, not just at the surface, but down into the root zone, climate models tend to disagree with one another. In fact, the projected trends in future drought are pretty bimodal, no matter which future scenario you're looking at. So this is a plot from a paper that my colleague Ben Cook and a bunch of collaborators, including me, put out in Earth's Future this year. And we looked at the risk of drought in the Southwestern North America under different scenarios, a sustainability scenario, a kind of middle of the road scenario, and a defensible business as usual, high emission scenario. And in all of these scenarios, what we saw was really sort of bifurcated drought risk, with some of the models being very, very high risk, saying we're going to see a lot more droughts like the one that we are currently in the future. Whereas some other models project no real increase in drought risk, and a few actually project that drought risk is going to decrease in the future. And this is not due to different rates of warming in the models. If you hark back to that slide that I initially showed, where different climate models have very different sensitivities, that translates into different rates of warming, with the high sensitivity models warming up very, very quickly, and the low sensitivity models still warming, but that warming being a little bit slower. But this is not due to different rates of warming in the models. These differences in the projections of drought aren't simply related to the model's climate sensitivity. In fact, we can divide these models into high-risk models and low-risk models. And we actually know what's going on physically here. So in the high-risk climate models, greenhouse gases force larger declines in springtime precipitation, but they primarily dry the soil moisture via warming. It's primarily a temperature-driven drying. Whereas in these low-risk models, the models in which the risk of droughts might even decrease in the future, yes, you still have temperature-driven warming, but in many of these models, greenhouse gases force increases in precipitation in the summertime. So the question is, who's right? Which is more credible? How do we make projections and plans for the future of the Southwestern North American continent in the presence of this model uncertainty? And what I would like to argue is that understanding the future requires us to understand what has happened so far. We need to understand the present drought, put it in context, and try to understand what's driving present drought conditions and what that can tell us about the future. So we know that the Western United States is currently experiencing a severe drought. This is not unprecedented. The paleoclimate evidence collected from tree rings indicates that the early 21st century megadrought is actually only the second driest period on record. But it's unusual because it appears to be forced. Previous work by Park Williams et al. That appeared last year in Science suggests that warming due to greenhouse gases is very likely to have contributed substantially to the current drought conditions. And something that always struck me was, why now? Greenhouse gases have been increasing pretty steadily since the Industrial Revolution. So why is it only in the 21st century that we start to see the signal of greenhouse gases really coming through in the drought conditions of the region? Moreover, something that was really surprising and confusing to me is if you look at this long-term paleoclimate record, yes, the current drought is extremely severe in the context of the paleoclimate evidence. But if you look at the 20 years, the 15 years, the couple decades before, those were actually the wettest decades on record from a soil moisture perspective. So those are my questions. What's going on? Why are we seeing such wild swings? And why now? Why are we only seeing the greenhouse gas signal now? So humans have emitted a large amount of greenhouse gases, and we know that those greenhouse gases have affected the climate. But those are not the only factors that have affected the climate. They're not the only what we call radiative forcings, external things that have changed the energy balance of the planet's climate. Humans have done more than just emit greenhouse gases, and nature has actually also affected the energy balance. So something nature has done and does periodically is set off volcanoes. There have been several large volcanic eruptions in the past couple centuries, starting, you can see Krakatoa here in 1883, fairly large, but more recently, Mount Agung, El Chichon in Mexico, and really notably, Mount Pinatubo in the Philippines in 1991. Now, certain volcanic eruptions emit huge quantities of sulfur dioxide, which reacts in the atmosphere to form sulfate aerosols. And this has a very well understood cooling effect. What you can see over here in the dashed line is the model, the projection of the GISS climate model for the impact of Mount Pinatubo on global average temperatures. And the solid line is the actual impact of Mount Pinatubo on global average temperatures. So we know that volcanic eruptions have the potential to change the climate. These changes are very large, but they're very temporary. The cooling goes away after a little bit. But that said, there have been several large volcanic eruptions clustered together. So when we're looking at externally forced climate changes, we need to take natural forcings like volcanoes into effect. Moreover, volcanoes aren't the only source of aerosol pollution that blocks the sun. Human activities emit pollution too. And we have coal-fired power plants, we have fossil fuels, we have transportation that emits what we call aerosol pollution. Basically, gas, dust, junk, particulate matter that gets into the atmosphere. Now, you can directly see one of the effects of aerosols. Aerosols on a bad air day block the sun. So we know that that is an effect of aerosols. They also do something else. Aerosols have a fairly powerful, if not completely well understood, indirect effect in that they tend to make clouds brighter and longer lived, like you can see here in ship tracks over the Pacific Ocean. Those are seeded by pollution trailing behind ships in their exhaust pipe, which contribute to making clouds brighter. So we know that both of these effects block the sun. Both of these effects alter the energy balance of the planet. And it's uncertain. We don't have a really good handle on exactly what aerosol forcing does. And that's because of these indirect effects, these cloud effects. But we are fairly sure that aerosol forcing was negative. Aerosol forcing has cooled the climate. And moreover, we know in large part where these aerosols are and have been coming from. Aerosol concentrations from North America and Western Europe increased after World War II until clean air legislation in both regions in the 1970s really leveled off that aerosol burden. And now the aerosol burden has largely shifted to East and South Asia and decreased in total magnitude. So we know that aerosols peaked around the 50s to the 80s, aerosol forcing. And interestingly, global soil moisture proxies actually show wetter conditions between 1950 and 1980. This is the time when aerosol forcing was at its peak. And in our 2019 paper, we found some tantalizing evidence that there might be a forced component to this because climate models mostly simulate moistening in response to aerosol forcing. But the aerosol fingerprint is extremely uncertain in climate models. And so in order to do any formal attribution, we really need to understand what that aerosol fingerprint actually is, what the climate does in response to aerosols. So how have these various external forcings, yes, greenhouse gases, but also land use change, volcanoes, aerosols, how have these different external forcings affected drought in the southwestern US? How can we separate the signal of each of these forcings from the noise of internal climate variability, the noise of what the climate would have done in the absence of any of these external influences? So what we wanted to do was to investigate the influence of these multiple external factors, these multiple external forcings, things that change the energy balance of the planet on the climate of Southwest North America. Now, we have observations of surface air temperature, precipitation, and 2-meter soil moisture that go back to 1901. And what we want to do is we want to figure out what is causing these variations, these year-to-year variations and these long-term trends. So this is June, July, August average surface air temperature. And you can see obvious variability here, an increase, a fairly steady increase with an interruption. Whereas precipitation, there's a lot of interannual year-to-year variability, maybe a few events clustered together in the 80s of high precipitation, but you can't really eyeball very many trends from that. Whereas the June, July, August, the summertime average 2-meter soil moisture, you can see very, very clearly that there was higher than average soil moisture in this region between 1985 and 2000, and lower than average soil moisture in 2000 and 2014. So drought and wet period here. So what was affecting these? What's affecting the climate? Well, we've got greenhouse gases, so that's anthropogenic increases in carbon dioxide, but also methane, nitrous oxide, HFCs. We've got aerosols, so particulate air pollutants, smoke, basically junk, gas and dust. Natural forcings, solar variability, which has been really small and pretty negligible over this time, but volcanic eruptions, particularly that giant whack of Mount Pinatubo in 1991. And then other external forcings, things like land use and land cover change, ozone depletion, but also interactions between these different forcings. And finally, we never forget the influence of internal variability, natural cycles, natural oscillations like El Nino and La Nina, the North Atlantic Oscillation, Pacific Decadal Oscillation. Basically the slosh of air and water around the climate system that leads to variability, even in the pre-industrial climate. Even if there were no human influences whatsoever, there would still be climate change on a year-to-year basis because there is this internal variability, this background noise. So we want to separate out the effects of each of these different forcings and internal variability. There's only two problems. Problem number one, we don't know the response to the external forcing. We don't have any observations of pure forced response because the observations that we have of the climate are a combination of the climate's response to whatever external forcing and internal variability. We also don't know the internal variability because we don't have any recent observations of an unforced climate. As long as we have been systematically observing the climate, we have also been changing it by emitting aerosols and greenhouse gases and changing the land surface. So we don't know the response to forcing. We don't know the internal variability. What do we do? Well, in order to do that, we need to turn to model simulations. We don't have the counterfactual of what would the climate be doing only with greenhouse gases, or what would the climate be doing without us. So to simulate those counterfactuals, we need to turn to climate models. So this is that CMIP6, the state-of-the-art climate models. And a sub-project of that is called the Detection Attribution Model Intercomparison Project. As part of this project, different modeling groups have performed single forcing simulations. So counterfactual simulations in which there is only natural forcing, solar variability and volcanic eruptions, or only aerosols, or only greenhouse gases. So this is a great and wonderful resource for us scientists to try to understand what the impacts of these various external factors are on, for example, regional soil moisture. There's just one problem. Climate models do not agree on the physics of what these external forcings, these external influences do to soil moisture. For example, in the Canadian Earth system model here, CAN-ESM5, in the Canadian model, soil moisture changes are very much driven by temperature. Not that much happens to precipitation in this model. And this means that aerosols moisten the soil because aerosols block the sun and they really make it cooler. They slow down the warming. Whereas greenhouse gases make it warmer, drive up evaporative demand, and this has a major drying effect on the soil. So in the Canadian model, aerosols make the soil wetter and greenhouse gases dry it. Whereas in the Hadley Center model based out of the UK, in this model, greenhouse gases provoke a very strong precipitation response. So greenhouse gases, I want to be clear, still make it warmer in the Hadley Center model, but they are also simulating a compensating, more than compensating increase in precipitation. So in this climate model, the effect of greenhouse gases is actually to moisten the soil, to make it wetter, whereas aerosols dry the soil. Clearly, both of these cannot be true. How do we differentiate between these different models? And how do we use multiple lines of evidence and keep track all of these different uncertainties? Uncertainties in the observations, uncertainties in forced responses, uncertainties in the unforced natural internal variability, which again, we do not know. To do that, we turn to methods first developed by the good Reverend Bayes. I am a really big fan of Bayesian statistics because for me, it's very intuitive. It's how our minds work. We start out with something we used to think, and then we look at the evidence. We say, how probable is the evidence given what I used to think? And we use that to construct a likelihood, which we then use to update our priors. So what we now think is what we used to think, updated in light of new evidence. This is the way science is supposed to work. This is the way our human brains work. It's the way we process information. However, when you do talk about Bayesian statistics, you always need to be careful to consider PC, the probability that you are using Bayesian statistics correctly. So Bayesian methods also provide, for me, very intuitive ways to differentiate between alternative models, alternative explanations of the world. So for example, consider two mental models of temperature variability. One, which I will call the US Senator model, posits that observed warming trends are solely due to internal variability. They're just noise. And you don't need to invoke any response to forcing in order to explain that. So that is model one, the US Senator model. There's also what I might call the scientist model, where observed warming is a response to external forcing plus internal variability. Now you can use the tools of Bayesian statistics to ask which of these models best fits the observations. So the US Senator model, in which the observations are just pure noise, is not a great fit. Whereas the scientist model, where the observations are noise and an underlying forced response, an underlying response to external factors, which are changing the energy balance of the planet, that's a better fit. So this is a very intuitive way of weighing different models. Now, in our case, we are considering the US Senator model. We are considering the it's just climate noise model. But we are also considering not just a model of response to a particular forcing, but we're considering responses to forcings generated by different climate models. So the question is, how well do those forced responses generated by different climate models represent the observed temperatures? And the answer is, a regression model with forced responses always outperforms pure climate noise in explaining the temperature, no matter which climate model is used to estimate those responses. And this is sort of statistics language for something that is very intuitive and very clear. Every single climate model says that there is a large response to external forcings in the temperature. The observations provide evidence that support that. It does not matter which climate model you use in order to generate those forced responses. Any climate model you use, any model you use that's worth its salt, that tells you something basically physical about the world, is going to give you a response to forcing, which is better able to explain the observations than pure natural variability. So every single climate model ranks above noise when it comes to explaining temperature variability in the region and globally, but right now we're focusing on the region. And as a result, you can take a weighted multi-model average where you are weighting each climate model based on its ability to reproduce what we see, to reproduce the observations. And you can come up with contributions of external forcing to temperature variability on a year-to-year basis. So what you can see here in the orange is the contribution of aerosols, that's sun blocking pollution, to temperatures in the region. And you can see it's pretty robustly negative. It's very, very, very small until post-World War II, 1950s, really starts to ramp up in the 1960s. And then it has a fairly persistent cooling effect on this region. Whereas greenhouse gases in the green, those have a persistent warming effect. Now, some years you get temperature variability that is above what you can explain just with external forcing. And we expect that. That is real because this model is the response to forcing plus internal variability laid on top of that. So when you take 15-year running means, that temperature anomaly, the warming that you observe between 1985 and 1999, greenhouse gases explain more than 100% of that temperature anomaly that you see, whereas aerosols are responsible for cooling. So during that time period, you've got a greenhouse gas induced warming signal counteracted by a strong aerosol cooling signal. Now, moving forward to the present day, greenhouse gases are still affecting the temperature. They are still making it warmer. In fact, they're making it even warmer, whereas aerosols are making it less cool. So the power of greenhouse gases to warm relative to the power of aerosols to cool is shifting. What about precipitation? We've seen that this region is subject to a lot of precipitation variability, and climate models are kind of all over the place in what they simulate there. So some climate models show a forced precipitation response that is not apparent in the observations. So some models, for example, the Hadley Center model, that UK model that I mentioned, projects a response to greenhouse gases that is a massive increase in summertime rainfall. We don't see that in the observations. They provide no support for that. Now, some other models say, no, there should be no response. We should not be able to see the influence of external forcing on the regional precipitation whatsoever. But in that case, instead of saying there is no forced response, why not just say it's all noise, it's all internal variability? And that's what we find. No climate model simulates a forced response that is better at explaining the observations than a simple model that considers the variability just noise. So in this case, that US Senator model for it's just a natural cycle, it's just natural variability, that is the best model for precipitation changes in the region. That does not mean in the future that there will be no effect on precipitation in the region. What that means is that the current precipitation variability provides no evidence for a forced response that is already apparent. So we detect no forced signal in the regional mean precipitation. What have greenhouse gases been doing to precipitation? Nothing that we can detect. What have aerosols been doing to precipitation? Nothing that we can detect. So the best explanation for precipitation variability, including the wet period, 1985 to 1999, and the dry period, 2000 to 2014, is just noise, is just internal climate variability. So to contrast, temperature in this region shows extremely robust evidence of external forcing. You cannot explain the regional warming without recourse to greenhouse gases and aerosols. Whereas regional precipitation, you can explain that just fine with what we know about pure natural variability. So what about soil moisture? Well, soil moisture, half of the climate models simulate responses that fit this better than pure noise, whereas half don't. And the half of the general circulation models, the climate models that give you results that are better than noise, are all telling you roughly the same thing. They're telling you that greenhouse gases have been drying the soil, and aerosols and volcanic eruptions have been trying to counteract that. So as a result, this dry period right now, the California drought, the Western US drought, we find that greenhouse gases definitely are contributing to that. Greenhouse gases contributed between 14% and 61% of this really, really anomalous dry soil moisture. Whereas aerosols are counteracting that. It's not as warm as it would have been in the absence of aerosols. And so we think aerosols contributed negative 13%. They counteracted that. Other forcings like land use change or interactions contributed in the same direction as greenhouse gases. But importantly, we are not saying that this current drought is solely due to external forcing. We're saying that external forcing certainly gave it a boost, but you need internal variability on top of that to explain how dry the soil moisture is. And that's understandable. There's always internal variability happening on top of a force signal. So how about this wet period, this anomalous wet period, 1985 to 1999? Well, we found that that wet period probably would not have been as wet were it not for the counteracting influence of aerosols and the Mount Pinatubo eruption. So we find that greenhouse gases were trying to make it warmer, and they were making it warmer during this time period, and that warming dries the soil. But at the same time, the counteracting temperature effects of aerosols and volcanic eruptions were acting against that greenhouse gas induced drying in order to moisten the soil. And so that is a partial answer for why now. Why is the greenhouse gas signal only emerging now? It's only emerging now because in large part, it was masked in previous decades by the counteracting evidence of the counteracting effects of aerosols and Mount Pinatubo. So to conclude, we think that greenhouse gases likely began to dry the soil moisture in Southwestern North America even before we noticed, even before the 21st century drought. And this, I think, is an argument, perhaps a provocative argument, that the emergence of this greenhouse gas force drought was delayed by moistening in response to aerosols and natural forcings. So if we had not emitted so much aerosol pollution, we may have seen this drought emerge earlier. We know from the evidence here, this is suggesting that external forcings have affected drought risk primarily through their influence on temperature and therefore their influence on evaporative demand away from the surface. We find no evidence, and this is actually commensurate with a lot of research. We don't find any evidence for an external influence on precipitation. We don't find any evidence that greenhouse gases are noticeably shifting precipitation in the region. And yet, because of that temperature signal, the temperature is drying, the warming is drying the region, even as precipitation remains largely unchanged. And what this means is that if you think back to those high-risk models projecting severe drought risk in the region going forward, and those low-risk models in which drought risk is counteracted by increases in precipitation, well, we don't find any evidence for an increase in precipitation. We don't find any evidence for a greenhouse gas-driven increase in precipitation. And as a result, this may mean that those higher risk models going forward into the future are giving us projections that are more credible. And I think this is important to keep in mind as we move forward to try to mitigate climate change, yes, but also to adapt to it. We are going to have to adapt to climate change. It's already here. We're already 1.2 degrees Celsius warmer than we were in pre-industrial times. We definitely need to take action to mitigate climate change, but climate change is already here and we need to know what's coming. We need to know what to deal with. And this is evidence that that signal was largely delayed. The emergence of the greenhouse gas signal, at least in the Western United States, was largely masked by aerosol pollution and Mount Pinatubo. And so going forward, this is sort of the real signal starting to emerge from the noise. So thank you very, very much for listening. I'm going to stop sharing my screen and I'm very happy to take questions.
Great. Thank you so much, Dr. Marvel. We have a couple of questions in the Q&A, and we'll start with those. And we have some thank yous in the chat. And so let's get started in the Q&A. So can you address the latest research on melting methane hydrates due to warming caused by the ocean thermal conveyor belt?
I mean, not really. What I can say is that, there is evidence for a slowdown of what we call the Atlantic meridional overturning circulation. That is basically a consequence of the Arctic is warming faster than anywhere else in the world. Because the Arctic is warming faster than anywhere else in the world, it is melting. We're seeing a lot of melting of land ice from Greenland, a big influx of fresh, cold water. That is slowing down, weakening the AMOC, the Atlantic Meridional Overturning Circulation. There is evidence that that is happening. So we do have evidence that for a circulation shift. When it comes to hydrates, I feel like every 3 years or so, the media gets really excited about a methane bomb. Sometimes it's permafrost, sometimes it's clathrates, and says, we're all doomed. This is definitely going to immediately put a bunch of methane in the atmosphere, and we're going to warm up like crazy. Not a lot of evidence from the paleo record for that happening in past warm climates. However, there are feedback processes to take into account. And those are largely taken into account by climate models. Those are not perfectly well constrained feedback processes, but that's definitely something that we take into account.
Great, thank you. Here's a practical question. Is there anything we could be doing that would mimic the effect of aerosols, but without the downsides?
So that is a real can of worms, and I'm going to get myself in huge trouble talking about that. So there are proposals to deliberately alter the planetary energy imbalance because we know that volcanoes can cool the planet. We know that aerosols cool the planet. And so the proposal is, what if we were the volcano? What if we did this deliberately? So this is called either solar radiation management, basically blocking the sun, or through stratospheric aerosol injection, which is basically, being artificial volcanoes, putting a bunch of jets up in the atmosphere and seeding it with sulfur dioxide, which will form sulfates in the stratosphere. There are huge governance concerns with that, huge ethics concerns with even doing research. And that's kind of beyond my pay grade as a physical scientist. As a physical scientist, though, would it cool down the planet? Yes, that would probably work. But if that should probably not be your only metric, is the global average temperature. In particular, there are asymmetries between warming up the planet by putting a bunch of carbon dioxide in the atmospheric column and cooling down the planet by blocking the sun. They're not exact opposites. In particular, we know that blocking the sun would probably reduce evaporation away from the surface. And that would have implications for the hydrological cycle, rainfall, evaporation. That's a huge can of worms, lots of things to think about, but it is an area of really active research within models right now. And a bunch of folks are starting to think about possible governance structures.
That's really interesting. And as one of the attendees said in the chat, so what could possibly go wrong? Okay, here's another one. Do forest fires contribute more aerosols or greenhouse gases? And should we expect soil moisture changes related to the Western forest fires?
Yeah, great question. So fires are very complicated because they are driven in part by climate change. We know that climate change is making fire weather more frequent and severe, those hot, dry conditions. And we know that that's been contributing to fires out west. Um, obviously, fires depend on land management practices as well, controlled burns versus just letting everything grow. They also depend on where people live, the damage that they cause. So fires aren't just a climate phenomenon. But that said, we do know that climate change is increasing fire weather. They also have a feedback effect because fires emit a lot of aerosols. There's a lot of smoke. I think all of us across the US experienced wildfire smoke. We certainly got it in New York City this summer. And that does have a sunblocking effect. But fires also destroy things that take up carbon dioxide. So fires are a source of atmospheric carbon dioxide. So it's all very complex. There are worries that in the future, we could cross tipping points with things like, for example, forests over the long term shifting from being sinks of carbon to being sources of carbon as they burn down.
That's great. And I'm looking at these questions. I realize we're going to keep coming back to the question of if we are the volcano. But in between, here are a few others. Is it still believed that there is a 10-year delay in the greenhouse gas release and the new point of thermal equilibrium?
I don't really know what that means. So when greenhouse gases are very well mixed in the atmosphere, so it doesn't matter who emitted them. We're all going to feel the effects. They're also quite long-lived in the atmosphere. So about 20% of greenhouse gas emissions in the atmosphere will linger for thousands, tens of thousands of years, and that's because greenhouse or CO2 is removed from the atmosphere by terrestrial processes like trees and plants. It's removed by the oceans. But that long-term stuff is really only removed by rock weathering. So CO2 is fairly long-lived in the atmosphere. Now, if you increase CO2 and you maintain that level, it takes the climate a very, very long time. So not 10 years to come into equilibrium, it takes the climate thousands of years to come into equilibrium. And that is because the ocean is very, very deep. Right now, the ocean is taking up about 93% of the excess heat that humans have contributed to the climate system. If the ocean were not doing that, we would not be like 1.2 degrees warmer, we would be about 40 degrees warmer, and it would be kind of game over. So a lot of heat is going into the ocean. And because the ocean is so deep, it takes a really, really, really long time for that ocean to come into equilibrium.
Wow, these answers just get more and more hopeful. Okay. In the Midwest, we experience megastorms that do not actually change annual precipitation, but redistribute it. Is there evidence for this with external forcing?
Yes, so there is pretty robust evidence for shifts in the characteristics of rainfall. In the Midwest, you get a lot of what we call mesoscale convective systems, so those big Midwestern thunderstorms. And there's evidence that those are going to be changing. But a really robust prediction of kind of the basic physics that underlies climate models is that warm air holds more water vapor. So the saturation vapor pressure increases as the temperature increases. And what that means is that there is more moisture in the atmosphere that can get dumped on us when it does rain. And so you're starting to see rainfall characteristics shift where you get maybe fewer, but certainly storms that dump more precipitation on you. That's something that we saw in New York with the remnants of Hurricane Ida. That was record-breaking precipitation. And that's something that has really been expected in a warming world.
Okay. And I love these people with good eyesight. Would you mind saying a few words about the book, All We Can Save, that is visible on the shelf behind you?
Sure, yeah. So this is the book that I was invited by my friends Ayana and Catherine to participate in. It's an essay collection where essays were written by woman identifying folks in the climate space. So there's a few scientists, myself, Catherine Hayhoe, Jane Zelikova, scientists that I really admire, but also activists, policymakers, political scientists, and it's very much focused on a lot of it is focused on solutions. So I think very highly of a lot of the folks included in that anthology, and I think it's definitely worth checking out.
Great, thank you. There was a rumor in science fiction writer Fred Pohl's book, Terror, that Pinatubo was the result of a deliberate, i.e. a test of concept or accidental effort from a geothermal project to set off the otherwise natural Pinatubo eruption. Would it matter that if Pinatubo, if Pinatubo was also human caused? Pohl was not all sci-fi. He also wrote a good book on Chernobyl and was consulted on possible projects with the US Defense Department.
I mean, like it's hard to debunk conspiracy theories, right? I mean, that sounds very much like a conspiracy theory. And if you say that doesn't sound right, it's, you're in on the conspiracy. So, there's no winning. We know where the mountain of Pinatubo is. We know that it exploded. Moreover, we know that volcanoes do this periodically. There's ample evidence for volcanic effects on climate throughout history. My personal favorite is 1815. Mount Tambora blew up. That led to what was called in the Northern Hemisphere the year without a summer. A teenage girl got trapped inside with a bunch of super insufferable men, and they started telling each other ghost stories. And one of those men was Lord Byron, who ended up writing a poem about vampires. But the teenage girl was Mary Shelley, and she wrote Frankenstein. So, Frankenstein arguably results from a volcanic eruption. So that's just to say there's ample evidence in the historical record for volcanic eruptions having a large effect on the climate.
Okay. And this is more of a comment, but you might want to comment on it. Blocking the sun would reduce photosynthesis and thus the autotrophic basis for life. So in thinking about that sort of engineering, how does this play into the thinking and the models?
I mean, that's certainly a consideration that, plants like sun. I like sun. And so, large scale blocking the sun might have effects on, plant photosynthesis and therefore plant productivity. In addition to that, if blocking the sun happens in conjunction with no effort to reduce emissions, then that does nothing about ocean acidification, for example, and in fact even makes it a little bit worse because ocean acidification is worse in colder temperatures. So there are. It would take hours and hours and hours to talk about the risks associated with geoengineering. I really recommend, if folks are interested, checking out the National Academy's reports. So the National Academies has been doing really interesting research direction reports on how we should think about these things. So not just solar radiation management, but also things like carbon dioxide removal. So, deliberately trying to pull carbon dioxide out of the air using terrestrial and ocean-based methods. And they actually just yesterday released their ocean-based strategic plan. So if folks are interested in these things, those are really well written, really accessible, and I really recommend checking them out.
That sounds great. And actually, it's a good lead into the next question, which is just to ask, does ocean acidification increase or decrease rock weathering?
I don't know. No idea.
Okay, that's good. Well, Could you say a little bit more about the National Climate Assessment and your work on that on the Trends chapter?
Sure. So the National Climate Assessment is mandated by Congress, supposed to come out every 4 years. In practice, does not come out every 4 years, comes out kind of random integer number of years after the last report. So the last report came out in 2018, NCA 4. And this is NCA 5, so attempting to build on the really great work that NCA 4 did on communicating climate change, what's going on, what we expect in the future, and what we can do about it. So we are tasked with being policy relevant, but not policy prescriptive. So we can't say, you should do this, but we can say, here are the considerations to take into account as you design adaptation and mitigation policy. And that's been a really interesting experience because it's the first thing I've done that has been deliberately very large scale and very public facing. So learning how to write for the public, learning how to write for policymakers is a real skill.
Well, you mentioned you were hoping to write a popular book. What will you write about, or what are you writing about?
So I'm working on a book right now called, working title is Human Nature. And it is the story of climate science told through emotions. So starting out with wonder, and then shame and fear and grief, but then going through to surprise and hope and love. So really trying to attack the stereotype that scientists don't have any feelings, and make the science really resonant, hopefully, for members of the public.
That sounds great. I will pre-order anytime. So we are not quite at the end of our time. If there are other questions, feel free to enter them in the Q&A, but I'm going to take my privilege and just ask, I wondered if you could say a little bit more about differences in models and why they happen. And so I noticed, you have a model that is a Canadian model and a UK model. Is place significant in explaining why some of these models come up with such different different interpretations?
Yeah, great question. So climate models are not trying to be perfect. They're trying to be useful. Because if you had a computer model that was able to simulate all aspects of life perfectly, that would be really creepy, right? Like that would be the Matrix. And so that's not what we're trying to do. Climate models are trying to simulate the entire Earth. And that means that we have to make some approximations. So for example, we know exactly how clouds form. On a small scale, you've got a bunch of water droplets or ice crystals, you have a dust grain, and that can make the water droplets coalesce around it, and boom, you get a cloud. So we know how that works. We understand cloud formation. But the problem is when you try to put that in a model of the entire Earth system, we can't track around every single tiny dust grain. We can't track around every single water droplet in the entire atmosphere. And so as a result, we have to make approximations. We have to do what's called parameterizations. So not just for cloud formation, but for any number of processes that happen on scales which are too small to explicitly represent in a climate model. So different modeling groups have different ways of representing those processes. And that's what gives you this diversity in projections going forward. If all of the climate models say the same thing, which they do, for example, you put greenhouse gases in any climate model and it will show warming, because that is just very, very basic, well understood physics. No doubt about that. So things that the climate models agree on are things where we understand really, really well what's happening. Things that the climate models disagree on that's exciting. That's science to do, because we can sort of dig in and say, well, what is happening? What do the observations say? What's the evidence? And what is the physics that describes what's going forward in the future?
Okay, thank you. Thinking, I mean, I really love the idea about thinking through climate change from the perspective of emotion. And one of the attendees says, I hope you don't mind, but I was very touched when I saw you cry on camera about climate disaster, and how much of a powerful and important message, tears and emotion can be. What led you to think about this approach to communicating about climate change?
I was thinking a lot about how we as scientists try to talk about what we do. And I think, there's a benefit in striving for, scientific truth, being very rigorous, always questioning what you're doing. But at the same time, I think pretending that we don't have emotions, pretending that we don't feel things, that's not objectivity, that's lying. And I think pretending that all of us are completely okay and we don't have preferences, and we don't care what's happening to the climate, we don't care what happens to the earth, that just strikes me as being dishonest. And I think we should have ways of talking about feelings. We should have ways of talking about the fact that we live here on this planet and it matters to us, that doesn't call into question our ability to do science.
Great, thank you. And I think this might be our last question. It says, are fractals, self-replicating patterns on many scales, used in these climate models? And are deep learning algorithms used?
So I use deep learning algorithms in a lot of my research. For example, I've got you can train a machine learning algorithm. Sorry for that. Let me just get this real quick. On paleoclimate data, and use that to sort of identify when signals of novel conditions started to emerge. You can also use machine learning algorithms, and people have started to do this, to train those parameterizations, those approximations. But I think it's important to remember that in a climate model, its guts are just physics. The guts of a climate model are just Newton's equations, F equals ma, mass conservation, energy conservation. So I think it's really important to emphasize that a climate model is very different than an economic model, or even a COVID model, because fundamentally the water droplets and the land surface and the ice in a climate model, those are all obeying physical laws that we understand pretty well.
Well, thank you so much. This has been an incredible presentation and a great way to end the semester. And I just want to thank you so much for your work and for sharing it, and for the plugs for other things that we can read and learn from. And I hope that you will come back again. And I want to thank all of our attendees also for coming and for your good questions. And we will look forward to seeing you again in spring semester, and we'll post the schedule as it shapes up on the IAS website. So thank you all. I hope you have a good end of the semester, and that your boots are ready for the snowstorm for tomorrow. And we'll see you in the even colder month of January or February. Bye, everyone. Thank you.
Thank you so much.